Good afternoon, everyone. I welcome you all for this today's session. As we know, we have already started the paper 2 part. The name of this, the first paper 2 is physical optics and electromagnetic waves, and we have already started the first unit, that is nothing but the interference, where we have studied what is light, what are the uh, theories of the light. Then we have discussed the characteristics of light, properties of light, everything we have studied in introductory part. And then we went for the interference, where we have studied what is interference and all. So yesterday we have studied the relation between path difference and phase difference. Then we have discussed principle of superposition, where we have studied the principle, the statement of that principle of superposition with the example. In detail we have studied. Then we have introduced the interference. What is interference? We know when two or more than two waves arrive at a point simultaneously in a medium, energy at that point gets modified, and that is what we call it as interference. So this part we have already studied in detail, where we have studied the conditions for getting the interference pattern and condition for the getting discrete fringe pattern as well. And then we studied the types of the interference. So basically there are two types of interference which we have discussed, and those are nothing but the constructive interference and destructive interference. And then we went for the interference in plane parallel thin film, where we have studied first what is plane parallel thin film. Then we have discussed a transparent thin film of a uniform thickness, which is bounded by two parallel surfaces. That is what we call it as a plane parallel thin film, isn't it? So we call a thin film of thickness in the range 0.5 micrometer to 10 micrometer, which can be considered as a thin film. And then with the example that when white light is incident on a thin film, different colors are seen. So it can be explained by considering interference between the light which is reflected from the top and the bottom surface of a thin film. So interference in the case of thin film takes place due to the first reflected light and number two, that is transmitted light. So for that purpose we have considered this particular thin film having the two surfaces. So one, this is nothing but the upper surface of this thin film, and this is nothing but the lower surface of this thin film. So when we allow the ray of light to fall on this particular thin film, that is AB is the incident light which falls on this particular thin film at a point B, then what happens? There will be a partial reflection and partial refraction. Okay, so whatever the light which is getting refracted through that particular plane parallel thin film, again it falls on the inner surface, that is of the lower inner surface of the lower surface of the thin film, and it gets again reflected, again it falls on the upper surface of the thin film, and it comes out of that particular thin film. So these are the two rays, that is BC and EF. So if we find the path difference between these two rays, that is BC and EF, then we will be able to tell whether that particular light or whether that particular thin film will appear bright or it will appear dark. So basically the brightness or darkness of that particular thin film depends upon the path difference between these rays. So for that purpose yesterday we have discussed it. This was the consideration, that is we have considered parallel sided transparent film of thickness T having refractive index N, which is surrounded by the air. We allow the ray of light AB, that is monochromatic light, to incident on the upper surface at an angle A, at an angle I. At point B, the light undergoes partial reflection in the direction of BC and partial refraction along BD. So the angle of refraction is R, and at D it is again partially reflected along DE and partially refracted along DI. So the reflected light DE is partially refracted and that is in the direction EF. So at last what we have done, we have calculated the path difference between the rays BC and BDEF. So how to calculate it? This was the consideration, where we have EN and VM. We have considered that it meets at a point G, then angle HGD, that we call it as an angle of refraction, and the path difference between the two reflected rays, we have written it as n of BD plus DN minus BN, and then we got this equation 1, and we know that refractive index is nothing but the ratio of sine of angle of incidence upon sine of angle of refraction. So with the help of that particular formula, we got refractive index, and that comes n is equal to Bn upon Ne, and so that we got Bn is equal to n into Ne. So this was the second equation. Then what we have done, we found the path difference, and that comes n of GD plus Dm is equal to NGM. We call this as an equation number 3. So when we consider the triangle that is BGM, then we can write from that angle cos R is equal to GM upon BG, where we know that this BG is nothing but the twice of the thickness of the thin film, that is 2T. So we can rewrite this particular equation as cos R is equal to GM upon 2T, and therefore we got the GM is equal to 2T cos R. So this was the equation number 4. Then we have considered that path difference is equal to, basically we can write from these equations that the path difference is equal to what we can write? We can write n into Gm. What we can write? Path difference is equal to n into Gm, and that we have written it as 2nt cos R. We call it as 2nt cos R, and we call it as an equation number 5. So the reflected rays BC suffers a path difference that is of lambda by 2 on reflection at B. So you just try to understand that whenever a ray of light travels from rarer medium and falls on the denser medium, at that particular time, whatever the reflected ray will be there will be a phase change, or there will be a phase difference, or we can say there will be a path difference that is of lambda by 2. The phase will be equal to pi, okay? The change of phase will be of pi, and the path difference will be, that can be introduced as lambda by 2. So this we have discussed yesterday in detail. Now, if you take help of these equations, then ultimately we come to the conclusion that is of net path difference between two rays BC and EF, and that we can write it as 2nt cos R minus lambda by 2. So now we came to the conclusion that when the film will appear bright, if this path difference is equal to m into lambda, that means 2nt cos R minus lambda by 2. If it is equal to m into lambda, then this film will appear bright. Again, this equation we can rewrite it as this. That means when minus lambda by 2 comes to the when taken it is to the right hand side, then it gets added. That means we can write it as plus lambda by 2, and therefore we can write 2nt cos R is equal to 2m plus 1 into lambda by 2, where m is nothing but 0, 1, 2, 3. So this is the first equation we got for the brightness of that particular thin film. Then when film will appear dark, when it will appear dark, if this path difference is equal to, that is 2nt cos R is equal to m plus 1 into lambda, where m is an integer, and therefore m plus 1 is also an integer. So, or we can rewrite it as, that is 2nt cos R is equal to m into this particular equation. That is equation number 7. So 2nt cos R is equal to m into lambda, m is equal to 0, 1, 2, 3, etc. So these were the conditions. Finally, we came to the conclusion, that is conditions for maxima, that is brightness. And we know that maxima occurs when optical path difference will be m into lambda. And if the difference in the optical path between the two rays is equal to the integral, it is equal to an integral number of full waves, then the rays will meet each other in phase. The crest of one wave falls on the crest on the other, and wave interfere constructively. And thus, when 2 mu t cos R minus lambda is equal to m into lambda, this will be an equation number 1, and the reflected rays will undergo constructive interference to produce the brightness or maxima at the point of their meeting. So here is the condition for brightness, and that is nothing but the 2 mu t cos R is equal to 2m plus 1 into lambda by 2. So this is the condition for maxima. Similarly, we came to the conclusion of that conditions for minima, that is darkness. What is the condition? We know that minima occur when the optical path difference is equal to 2m plus 1 into lambda by 2. If we have the path difference 2m plus lambda by 2, then the minima will occur. and if the difference in the optical path between the two rays is equal to an odd integral number of half waves, then the rays will meet each other in opposite phase. The crest of one wave falls on the trough of the other and the wave will interfere destructively. So when 2 mu t cos r minus lambda by 2 is equal to 2m plus 1 into lambda by 2, that is an equation number 3, we wrote it, and the reflected ray undergoes destructive interference to produce the darkness. So equation 3 can be rewritten as 2 mu t cos r is equal to m plus 1 into lambda by 2, and the phase relationship of interfering waves does not change if one full wave is added to or subtracted from any of the interfering waves. And therefore m plus 1 into lambda can as well be replaced by m into lambda for simplicity in expression. And thus 2 mu t cos r is equal to m into lambda. This is nothing but the condition for darkness. So all these things we have studied in detail yesterday. Now today what we are going to study, that is nothing but the interference in thin film due to transmitted light. Now due to transmitted light, how the interference takes place, that we have to study today. So for that purpose, what we have considered, we are considering a thin film of thickness T again, having the refractive index N as shown by this particular figure. A ray of light AB is allowed, that is of monochromatic light, is allowed to fall on this particular upper surface of the thin film at a point B at an angle I. It is partially get refracted along BD. Now reflected ray we are not going to consider here. We are only considering the partly refracted light, and that is nothing but the BD. The angle of refraction is R. At D, it is again partially reflected. If you look at this particular figure, then you will be able to understand that this BD, when falls on the inner surface of this thin film, again it gets reflected into DE. Again it falls on the inner surface of the upper surface. Again it gets reflected and it falls on the lower surface, and then it gets transmitted through it in the form of FK. So this is the consideration. Hope you understood it. Anybody is having doubt here? Am I audible? Is the slide visible? Dear student, just unmute yourself and tell me.
Yes, sir.
Am I audible?
Yes, sir.
Okay. So the ray DE now, see, now we are talking about this DE. The DE after reflection at a point E finally emerges along FK. So if DM and FN we consider as a perpendiculars drawn to the EF and DI respectively, then it will produce FE and DH, which will meet at point G. So this will produce this FE, this FE, and this DH. See, this DH, this DH, they are meeting each other at this particular point G, and there is no phase change due to reflection. Already I told you, when a ray of light travels from rarer medium to denser medium, there will be a phase change, there will be a path difference, or we can say that is path difference actually. But when a ray of light traveling from same medium, either denser medium or rarer medium, then there will not be that is specially there will not be a phase change due to reflection at this particular point D and E, both of which are at a rarer medium. Okay, so this is the point for you to understand. So this is the consideration. Again, I'll show you. This is the ray of light which is falling at a point B. When falls on this particular, that is thin film, then again what happens? Partial refraction will be there, and that is nothing but the ray BD. When this BD falls on the inner surface at point D, again it gets reflected. It gets reflected here. It falls on the inner surface of the upper surface of the thin film. Again it gets reflected, isn't it? And here again it will get transmitted at this particular point D, and later on this EF gets transmitted through this particular thin film, that is in the form of FK. Okay, so this is the consideration. Now therefore the path difference between the two transmitted rays. Which are the two transmitted rays? One is the DI and another, that is FK. So we need to find out the path difference between these two transmitted rays. So the path difference will be, see, there is a path difference. That means when this F reaches at a point K, we can say, okay, when F reaches, or we can say let this D, when a ray of refracted light from D reaches at N, then what happens? This reflected light will reach at E, then it will fall on this inner surface at F, and then it will come out. So there is a phase difference, there is a path difference. Okay. So likewise, we can write here N of DE plus EF. This DE, which DE? This DE plus EF minus you will have to deduct DN. अगर इसमें से आप DN minus करते हो, so that will be the path difference between DI and this FK. So here later on we can write N of DE plus EM plus MF, because this EF is nothing but the EM plus MF. Okay, so directly we can write it as DE plus EM plus MF minus DN. Again, we know what is refractive index. I told you that refractive index is nothing but the ratio of sine of angle of incidence to the sine of angle of refraction, and that we can write it as, we know sine of angle of incidence, we can write it as dN, okay, dN upon dF. This will be the sine of I, and this is the angle of refraction. Therefore, sine R can be written as MF divided by dF. So we'll have the refractive index dN upon dF upon MF plus upon dF. So ultimately here dF will get cancelled, and we can write it as dN upon MF. So we'll get the dN is equal to N into F. Okay. So here the path difference will be, again here I'll tell you, if you solve this, then the path difference comes N into GM. Okay. And in the triangle DGM, if you consider triangle DGM, again here GM upon 2T is equal to cos R, or GM is equal to 2T cos R, we can write. And therefore, we'll have the path difference, that is N into GM is equal to 2NT cos R. So this is an equation number 1. So when the film appears right here, if 2NT cos R, M cos R is equal to M into lambda, where M will be equal to 0, 1, 2, 3, etc. The film will appear dark if 2NT cos R is equal to 2M plus 1 into lambda by 2, which I have shown by the equation 3, where here M will be equal to 0, 1, 2, 3, etc. So the conditions for transmitted light are just opposite to those for the reflected system. Just try to understand. If you remember, I just shown you the derivation for the interference due to the reflection, where we have considered that when film appears dark for the reflection of light due to the reflection, when the path difference is equal to M into lambda, and when it appears bright, when the path difference is equal to 2M plus 1 into lambda. That means the interference in thin film due to the reflected light and the interference in a thin film due to the transmitted light are opposite to each other. That means in another way we can say the conditions for transmitted light are just opposite to those for the reflected system. Hope you understood this. So here, thus we can say it is seen that conditions for brightness and darkness are exactly opposite for transmitted and reflected rays. It means the band seen is bright due to the reflected rays, that appear dark due to the transmitted rays, and vice versa. Hence, these two systems are said to be complementary. If you are asked, why do we call these two systems complementary? So this is the answer here, that it is the conditions for brightness and darkness are exactly opposite for transmitted and reflected rays. And that is why we call these two systems complementary. Okay, anybody having doubt? Yes, student, anybody is having doubt here now? How the interference takes place due to reflection in thin film, and how the reflection takes place, interference takes place due to the transmitted light. Hope you understood it. Shall I move on? Okay.
Yes.
Now let us move on to the next topic, and that is nothing but the phase change on reflection. How the phase change? takes place, or how the phase changes on reflection. Already we have studied that when a ray of light is reflected at the surface of a medium which is optically denser than the medium through which the ray is traveling, isn't it? So a change of phase equal to pi, or path difference, that is lambda by 2, is introduced. That is another way we can say, when a reflection takes place at the surface of a rarer medium, there will not be any phase change or path difference. There will not be any phase change or path difference. That means no change in phase or path difference takes place. So here we have the consideration where we have considered PQ be the surface which is separating the denser medium, below it from the upper, that is rarer medium, above it, as shown by this particular figure, a ray of light, this AB is a ray of light of amplitude A, incident on this particular surface PQ at a point B, which is partly getting reflected and partly getting refracted. So here BC is nothing but the reflected ray, and this BD is nothing but the refracted ray. That means when this monochromatic ray of light AB falls on this surface PQ at point B, then there will be a partial reflection and partial refraction. Okay, that is here if we consider R as the coefficient of reflection. What we have considered R, small r, we are considering as coefficient of reflection at the surface of a denser medium. This is the surface of denser medium, and at this point we are considering R as the coefficient of reflection at the surface of a denser medium, that is the fraction of the incident light which is reflected. Then amplitude of the reflected ray, that is BC, we can write it as AR. So that's why just try to understand. The incident ray is having amplitude A, and reflected ray I have written as A into R. Okay, what is the amplitude of the reflected ray BC? That is A into R, because I have introduced the coefficient of reflection. If T is the coefficient of transmission, now you just try to understand what is the coefficient of reflection and what is the coefficient of transmission. So the reflection coefficient is a parameter that describes how much of wave is reflected. What is the reflection coefficient? It is the parameter which describes how much ray is reflected. That is nothing but the coefficient of reflection. Now, what is the coefficient of transmission? Coefficient of transmission is a measure of how much of an electromagnetic wave passes through a surface or that particular optical element. Are you getting me? Hope you understood what is the coefficient of reflection and what is the coefficient of transmission. Okay, so if T is the coefficient of transmission from the rarer into the denser medium, that is the fraction of the incident light which is transmitted, then we can write again amplitude of the refracted ray as, that is AT. So that's why I have taken amplitude of this particular refracted ray, that is AT. Okay, understood? Incident ray is having amplitude A, reflected ray is having amplitude AR, and refracted ray is having amplitude A into T. If there is no absorption, if here there is no absorption, so directly we can write R plus T is equal to 1. So if the reflected and refracted rays are reversed, if this reflected and this refracted rays are reversed, the resultant should have the same amplitude. Try to understand. If you reverse these two rays, this reflected ray and this refracted ray, then what will happen? The resultant will have the same amplitude, that is A, as that of the incident ray. Amplitude will be A. So when CB is reversed, when we are reversing CB, it is partially reflected along BA and partially refracted along BE. Partially refracted along this BE. It is partially refracted along BE. So the amplitude of the refracted ray along BE, along this BE, will be ART. What will be the amplitude? that will be A into R into T. Similarly, when dB is reversed, when this dB is reversed, okay, when dB is reversed, it is partly refracted along this BA, it is partly refracted along BA and partly reflected along BE, partly reflected along BE. So if R dash is the coefficient of reflection at the surface of a rarer medium, then amplitude of the reflected ray along BE, we can write it as ATR dash. What we can write? Amplitude of the ray along BE, we can write it as ATR or AR dash into T. And if we consider T dash is the coefficient of transmission from the denser into the rarer medium, then the amplitude of the reverse refracted ray that is along BA, that this BA, that will be A into T dash. Okay, so the two amplitude, that is BA, will combine together to produce the original amplitude. These two amplitudes will combine together and it will give you this amplitude A. Okay, therefore we can write ART plus AR dash T, that will be equal to 0. Okay, and we'll have, if we combine these two, or we can write from this equation, that is ART is equal to minus of AR dash T. In another way, we can write it as R is equal to minus R dash. And from that equation, I'll show you here. See, this is the consideration. Already I told you, I have discussed you, and I told you that amplitude of the reflected ray will be equal to A into R. BC we have discussed. Then I told you that amplitude of the refracted ray BD will be equal to A into T. If there is no absorption of light, then R plus T will be equal to 1. And then this amplitude of the refracted ray along BE, that is, I have taken it as ART. Later on, I am telling you that I told you as well, when I discussed this consideration, that amplitude of the reflected ray along BE, we are moving back now, that will be equal to ATR dash. Okay, so if R dash is the coefficient of transmission from the denser into the rarer medium, then amplitude of the reverse refracted ray along BA can be written as ATT dash. Okay, so the two amplitudes along BE will combine together to produce the original amplitude only if the total amplitude along BE is 0. And therefore ART plus AR dash T will be equal to 0. Let us consider this is an equation number 1. In such a case, AR square plus ATT dash is equal to A. Let us consider this is an equation number 2. And therefore equations 1 and 2 are known as Stokes relations. And from equation 1, see, we have to only consider equation 1. What we can write from equation 1? We can write that ART is equal to minus of ART, where this A, T and T will get cancelled, and we'll have R is equal to minus of R dash. So what does it mean? It means that the negative sign shows here when one ray has a positive displacement, the other has a negative displacement. What this equation shows? It shows that the negative sign, when one ray has a positive displacement, the other has a negative displacement. And hence, the two rays, one reflected in reaching a denser medium and the other reflected on reaching a rarer medium, differ in phase by pi from each other. So this is the conclusion of this particular topic, and that is nothing but the phase change on reflection. So this is how the phase changes. This is how the phase changes on reflection. Anybody is having doubt here? I'll take your doubts at the end of this particular lecture. Now, colors in thin film. Okay. Now see, when white light is incident on a thin film, the light rays are reflected from the top and bottom surfaces of the film. Already we have discussed. When white light is incident on a thin film, the light rays are reflected from the top and bottom surfaces of the film. The condition for brightness or darkness depends upon one, that is refractive index, thickness of the film, where T and R are constant. White light contains a number of wavelengths. Already we have discussed. White light is composed of waves of different wavelengths. That is different colors. Because we know as the wavelength changes, the color of the light also changes. That means, in fact, we can say the color of light depends upon the wavelength. As the wavelength changes, the color of light also changes. So white light contains a number of wavelengths, that is N, for each color is different. Refractive index for each color will be different. Now, condition for brightness in the reflected system is 2nt cos R is equal to 2m plus 1 into lambda by 2. The color for which this condition is satisfied will be present with maximum intensity. Other colors in its neighborhood will have lesser intensity. It will have lesser intensity. Colors for which the condition of darkness 2nt cos R is equal to m into lambda, it's satisfied, will be absent, and therefore the film will appear color. When the film will appear color, colors for which the condition of darkness 2nt cos R is equal to m into lambda, if it is satisfied, it will be absent, and therefore the film will appear colored. Okay. Now let us solve some numericals. We have the first numerical where we have taken a parallel beam which is of sodium light having wavelength 589 into 10 raised to power minus 9 meter. It incident on a thin glass plate having the refractive index that is 1.5, such that the angle of refraction into the plate is 60 degree. We are asked to calculate the smallest thickness of the plate which will make it appear dark by reflection. What we have to do? We have to calculate the smallest thickness of the plate which will make it appear dark by reflection. So what is given here? We are given lambda, that is wavelength of the sodium light, that is 589 into 10 raised to power minus 9 meter. We are given the refractive index of the thin glass plate 1.5 and the angle of refraction 60 degree we have given. So for a dark band in the reflective system, already we know, we have learned the condition, and that is 2nt cos R is equal to m into lambda. So for the least thickness of the plate, we take m is equal to 1. Therefore, for the film to appear dark, the smallest thickness T is given by 2nt cos R is equal to lambda, or we can write this equation as T is equal to lambda upon 2n cos R. And here lambda, already I told you that it is 589 into 10 raised to power minus 9 meter given. Refractive index that is given 1.5 and the angle of refraction that is given 60 degree. So when you substitute all these values in this equation, that is T is equal to lambda 2n cos R, then you will be able to find the answer. And here the thickness of the plate, will be 392.7 into 10 raised to power minus 9 meter. Okay, so it will make it appear dark by reflection, isn't it? What we have done, we have found the thickness, that is the smallest thickness of the plate which will make it appear dark by reflection. So this is how we can solve the numericals. Let us move on to the next numerical. We have given white light which incident on a soap film at an angle that is sine inverse in bracket 4/5, and reflected light is observed with a spectroscope. It is found that two consecutive dark bands correspond to wavelength, that is 6.1 into 10 raised to power minus 7 meter and 6 into 10 raised to power minus 7 meter. If the refractive index of the film is 4/3, then we are asked to calculate the thickness. So here, let us consider m and m plus 1 be the orders of the consecutive dark bands for wavelengths lambda 1 and lambda 2. then 2 nt cos r, we can write it as m into lambda 1. This is the path difference for first. Let us consider this is an equation number 1. And second, that is 2 nt cos r is equal to m plus 1 into lambda 2. Let us consider this is an equation number 2. So, or this equation can be written as or m into lambda 1 is equal to m plus 1 into lambda by lambda 2. M is equal to lambda 2 by lambda 1 minus lambda 2. So when you substitute values, that is of lambda 1 and lambda 2, that is 6 into 10 to the power minus 7 and 6.1 into 10 to the power minus 7 and 6 into 10 to the power minus 7. Then the answer will be 60. So to find now cos r, we will have sin I, that is given 4 by 5, and refractive index, that is 4 by 3. So we know n is equal to sin I upon sin r, and therefore from that equation we can write sin r is equal to sin I upon n. So sin I already given, that is 4 by 5, and n that is given 4 by 3. So sin r will be equal to 0.6. So now therefore we can write cos r is equal to 1 minus sin square r to the power 1 by 2. So that cos r also we will be able to find, and that will be equal to 0.8. So now 2 nt cos r is equal to m into lambda. This is our n. What we want to find out? We have to find out the thickness here. Already I told you that we want to find out the thickness. So how to find out the thickness? Thickness can be found from this particular equation, because 2 nt cos r m into lambda, this is nothing but the condition. This is nothing but the condition which we have already learned. We have already learned in theoretical part. So if this 2 nt cos r is equal to m into lambda, therefore t can be written as m into lambda 1 upon 2 n cos r, because we are considering lambda 1. This is lambda 1, because already given it is found that 2 consecutive dark bands correspond to wavelengths. These are the 2 corresponding wavelengths. So if the refractive index of the film is 4 by 3, then we have to calculate the thickness, and that thickness will be 1.72 into 10 raised to power minus 5 meter. So this is how we can solve the numericals. Hope you understood this particular part. Okay, if you have any doubt now, you can ask me.